This is the EdExcel AS Level Maths Paper 2 from the June 2018 series, and this paper covers the statistics and mechanics modules. Question number 1. A company is introducing a job evaluation scheme. Points X will be awarded to each job based on the qualifications and skills needed, and the level of responsibility. Pay, Y pounds, will then be allocated to each job according to the number of points awarded. Before the scheme is introduced, a random sample of 8 employees was taken, and the linear regression equation of pay on points was Y equals 4.5x subtract 47, and for part A we have to describe the correlation between points and pay. Well, because we have a positive gradient here, as x increases, y would also increase. And so here for part A, we have a positive correlation. And then for part B, we have to give an interpretation of the gradient of this line of regression. Well, we can see that for every extra point, that would give £4.50 more on pay. And then for part C, we have to explain why this model might not be appropriate for all jobs in the company. Now, for part C, if I take a look at my equation y equals 4.5x subtract 47, we need to find out the value of x for which we would have negative pay. And so what we can do is set y equal to 0, and that would give 4.5x subtract 47 equals 0. And so what we have then is 4.5x equals 47, and therefore if I attempt to solve for x, 47 divided by 4.5, that's 10.44, etc. What we can see then for points less than 11, we're talking whole numbers here, it would give negative pay, which is ridiculous. Question number 2. A factory buys 10% of its components from supplier A, 30% from supplier B, and the rest from supplier C. It is known that 6% of the components it buys are faulty. Of the components bought from supplier A, 9% are faulty, and of the components bought from supplier B, 3% are faulty. And what we have to do is find the percentage of components bought from supplier C that are faulty. Now, the best way to do this question for part A is to draw a tree diagram. So we've got 3 events A, B and C, and for each of those events the components are either going to be faulty or not faulty. Now we know from the question that 10% are from A, so we've got 0.1 here. 30% are from B, so we've got 0.3 here, and the rest are from C, so 1 subtract 0.3 subtract 0.1, that's 0.6, so we've got 0.6 for C. And we know that from A, 9% are faulty, so here we've got 0.09, and we know from B we've got 3% which are faulty, so here we've got 0.03, and let's say we've got percentage P which are faulty for C. And so for not faulty from A, we'd have 0.91. Not faulty from B, that will be 0.97. And not faulty from C, that will be 1 subtract P. And so therefore, what we need to do is recognize that 6% in total are faulty, and so therefore the probability that the components are faulty, that's 6%. Now how could we get faulty components? We've got A being faulty, so that's 0.1 times 0.09. Then we've got B being faulty, so that's 0.3 multiplied by 0.03. And then we've got C being faulty, so that's 0.6 multiplied by 0.6 multiplied by P. And this is equal to 0.06. We know from the question that 6% of the components are faulty. So what we need to do is find out what P is. So we have 0.018 plus 0.6p equals 0.06. 0.6p is equal to 0.042. P is equal to 0.07. And then a component is selected at random. We have to explain why the component was bought from supplier B is not statistically independent from the event the component is faulty. Now we know for independent events the probability of A and B is equal to the probability of A multiplied by the probability of B. So for independent events the probability of A and B is equal to the probability of A times the probability of B. Now the probability that we select something from B and it being faulty, well, that's 0.3 times 0.03. And if we work this out, we get 0.009. And what we can also find out is the probability of getting something from supply B and the probability that it being faulty. So probability of supply B, so that's 0.3, and probability that it's faulty, well, we know that's 0.066%. And so if we work this out, we get 0.018. And what we can see from here then is the 0.009 does not equal 0.018. And so the events are not independent. Question number 3. Nazir is playing a game with two friends. The game is designed to be a game of chance, so that the probability of Nazir winning each game is a third. Nazir and his friends play the game 15 times, and for part A we have to find the following probabilities. And before we do anything else, we need to recognise that the number of events is fixed. We've got 15 times the game is played, and each trial is independent, and so we'd have to use a binomial distribution. So we begin by letting the random variable n equal the number of games Nazir wins, and with our binomial we can say that n follows the binomial distribution with parameters 15 and 1/3. Now for the first part of part A, we are finding the probability that n is equal to 2. And if we calculate this probability, we can use our calculator. If we go to the distribution section, we have binomial PD, select 2 for variable, we've got x equaling 2, n equaling 15, and p equaling 1/3. And so calculating this, we end up with 0.0599 given to 3 significant figures. And for the next part, the probability that he wins no more than 5 games, that's the same as the probability, well, he wins no more than 5. And so here, n is greater than 5. And that's equivalent to the probability, 1 minus the probability that n is less than or equal to 5. So if we calculate this, we've got 1 minus now here. We need to go to the binomial CD sub-menu. X here this time is 5. And so what we can see then is we've got 1 minus 0.618, etc. And if we calculate that to 3 significant figures, we end up with 0.382. Now, for part B of the question, Nazir claims that he has a method to help him win more than 1/3 of the games. To test his claim, the 3 of them played the game again 32 times and Nazir won 16 of these games. We have to state our hypotheses clearly to test Nazir's claim at the 5% level of significance. Well, for part B, our null hypothesis H0, that's P equaling 1/3. And so our alternate hypothesis, because we're testing whether we win more than 1/3 of the games, that would mean P is greater than 1/3 for our alternate hypothesis. And what we will do here, we will let the random variable x equal the number of games won. Now, we've got 32 games played. So, x follows a binomial distribution with parameters 32 and 1/3. And we see that Nazir won 16 of the games. So, if I calculate the probability that x is greater or equal to 16, and the reason for this is because the direction of the inequality matches. If I calculate this probability, well, this is the same as 1 minus the probability that x is less than or equal to 15. And so calculating this, again, with the distribution sub-menu, we've got 15 for x, n equaling 32, and p equaling 1/3. So we've got 1 minus 0.962, etc., which is equal to 0.0377 to 3 significant figures. And because this value is less than the 5%, what we can do is therefore reject H0. And so what we can do then, we can conclude that there's evidence to support Nazir's claim. Question number 4. Helen is studying the daily mean wind speed for Cambronne using the large dataset from 1987. The data for 1 month are summarized in table 1 below. And for part A, we have to calculate the mean for these data. Well, from our calculator, if we go to the statistics sub-menu, and then press number 1. We need to make sure that the frequency is on. So we can ignore this wind speed, and then for the rest of them, we've got 6. Then we've got 7, 8, 9, 11, 12, 13, 14, and 16. And then we've got 2, 3, 2, 2, 3, 1, 2, 1, 2. And then if we press options, then number 2, we can calculate the mean straight away. For the first part then, the mean, we'll call it x bar, that's equal to 10.2 to 3 significant figures. And then to calculate the standard deviation, that's equal to sigma x, which is equal to 3.17 to 3 significant figures. And we also have to state the units. Well, the units here would be knots. Now for part C, the mean and standard deviation of the daily mean wind speed for the other months from the large data set for Cambron in 1997 are given in table 2 below. The data are not in month order, and using your knowledge of the large data set, we have to suggest giving a reason which month had a mean of 11.57. Well, we've got a reasonably high mean over here for this particular month of E, which is 11.57, and the windiest month is most likely to be in autumn, so that would suggest that we have something in October. So, using the large data set, the month would be October because it's windier in October, which is in autumn. Question number 4, part D. The data for these months are summarized in the box plots on the opposite page. They are not in month order or the same order as in table 2. And for the first part of part D, we have to state the meaning of this star symbol on the box plots. So if I take a look at the box plots, we've got this star symbol over here. And what we have to do is state what those mean. Well, for the first part of part D, those quite simply mean outliers. And now we have to suggest giving your reasons which of the months in table 2 is most likely to be summarized in the box plot marked Y. Now, the way I will approach this is to label each box plot. So we'll call this 1, 2, 3, 4, and 5. And I'm just going to be referring to these box plots throughout my answer. Now, if we take a look at table 2, and if we take a look at B, C, and D, they all have means of 8 point something. These means are actually pretty close to each other. And if we take a look at these box plots, we can see that 2, 3, and 4 have medians close to each other. So let's write that down. B, C, and D have means close to each other, and box plots 2, 3, and 4 have medians close to each other. Now, if we take a look at Y, it's got this outlier over here. So, Y has an outlier, and we know that the mean is affected by outliers. And if we find the range of Y, including this outlier, then we can see Y has largest range, including the outlier, and so therefore we expect it to have the largest standard deviation. And so if we go back to our table, and if we take a look at these standard deviations, we can see B has a larger standard deviation compared to C and D. As we have written over here, and therefore Y could be month B. Question number 5. A biased spinner can only land on one of the numbers 1, 2, 3 or 4. The random variable x represents the number that the spinner lands on after a single spin, and the probability that x equals r is equal to the probability that x equals r plus 2 for r equaling 1 and 2. But given that the probability that x is equal to 2 is 0.35, and with this we have to find the complete probability distribution of x. So, first of all, if I use this equation here, when r is equal to 1, the probability that x equals 1, that's equal to the probability that x equals 1 plus 2. So we've got 1 plus the 2. So that's the same as the probability that x is equal to 3. And if I take a look at the situation for r equaling 2, the probability that x equals 2, that's equal to the probability that x is equal to 2 plus 2. So that's equal to the probability that x is equal to 4. And if we go back to the question, we know that the probability that x equals 2 is 0.35. So here we have 0.35. And therefore, we know probability adds up to 1. So we've got the probability that x equals 1 plus the probability x equals 2 plus the probability that x equals 3 plus the probability that x equals 4 is all equal to 1. So we've got the probability that x equals 1 plus the probability that x is equal to 2, which is 0.35, plus the probability that x is equal to 3, plus the probability that x is equal to 4, which is the same as the probability that x equals 2, which is 0.35. This is all equal to 1. And what we can say then is the probability that x equals 1 plus the probability that x equals 3 is equal to 1 minus 0.7, which is 0.3. And because the probability that x equals 1 is equal to the probability that x equals 3, we can therefore conclude the probability that x equals 1 is equal to the probability that x equals 3, which is 0.15. And so we have enough information to complete our probability distribution. So for our probability distribution, we've got x, and the probability that x is equal to x, we've got 1, 2, 3, and 4. And then the probabilities, we've got 0.15, 0.35, 0.15, and 0.35. Next, for part B, Ambro spins the spinner 60 times, and we have to find the probability that more than half of the spins land on the number 4. Give your answer correct to 3 significant figures. Well, for part B, if we let the random variable a equal the number of times the spinner lands on 4, again each event is independent and we've got a fixed number of trials, we can therefore conclude that A follows a binomial distribution with parameters 60, because it's spun 60 times, and the probability that lands on 4 is 0.35. Now, we want the probability that more than half of the spins land on 4, so that corresponds to the probability that A is more than 30. Of course here, more than half, that's half of 60, which is 30, and we want more than that, so we have A being greater than 30. And if I calculate this, that's 1 minus the probability that A is less than or equal to 30. And so if I calculate this, we can go to the distribution sub-menu. We have a binomial CD. X is 30. N is 60. P is 0.35. So we've got 1 minus 0.994, etc. And if I work this out, we get 0.00589. And that's given to 3 significant figures. Now, for part C of the question, the random variable y is equal to 12 over x, we have to find the probability that y minus x is less than or equal to 4. So, for part C of the question, we know that y is equal to 12 over x. And so therefore, if we have the probability that y minus x is less than or equal to 4, then this is the same as the probability that 12 over x minus x is less than or equal to 4. So we've got the probability of 12 minus x squared being less than or equal to 4, which is the same as the probability that x squared plus 4x minus 12 is greater or equal to 0. And I can factorize this. I've got the probability that x plus 6 multiplied by x minus 2 is greater or equal to 0. And this is going to be the probability that x is greater or equal to 2. And that's because x is greater than 0. Now the probability that x is greater or equal to 2, that's equal to the probability that x equals 2 plus the probability that x equals 3 plus the probability that x equals 4. And if I add these together, I've got 0.35 plus 0.15 plus 0.35, which is 0.85, which is what I want. Question number 6. A man throws a tennis ball into the air so that at the instant when the ball leaves his hand, the ball is 2 meters above the ground and is moving vertically upwards with speed 9 meters per second. The motion of the ball is modelled as that of a particle moving freely under gravity, and the acceleration due to gravity is modelled as being of constant magnitude 10 meters per second squared. The ball hits the ground t seconds after leaving the man's hand, and using the model, we have to find the value of t. Well, here is a sketch of the situation. We've got a tennis ball which moves vertically upwards. From the point where it was thrown, we're 2 meters above the ground, and we have to find the time when it hits the ground. Now, if we take this to be our 0 level, then the displacement will be -2 from here to here. So it goes upwards and then it goes down back to the ground if we take this point as the origin. Now, the SU that we will be using is S equals UT plus a half AT squared. And so, using S equals UT plus 1/2 AT squared, we've got -2 equals U, which is 9, times by T. Now, we subtract 1/2 times by 10. G will be -10. and then we multiply this by t squared. And so we've got -2, that's equal to 9t minus 5t squared. Rearranging 5t squared, subtract 9t plus 2 equals 0. If we factorize, we have 5t plus 1 multiplied by t minus 2 equals 0. So either t is equal to -1/5 or t is equal to 2. And so therefore, our value of t we require is 2, and that's because t must be greater than 0. Question number 7. A train travels along a straight horizontal track between two stations A and B. In a model of the motion, the train starts from rest at A and moves with constant acceleration 0.3 meters per second squared for 80 seconds. The train then moves at constant velocity before it moves with a constant deceleration of 0.5 meters per second squared, coming to rest at B. And for this model of motion of the train between A and B, for the first part of part A, we have to state the value of the constant velocity of the train. Well, if it starts from rest and then accelerates at 0.3 meters per second squared for 80 seconds, then for part A, if we use the suvat v equals u plus at, then we have v equals 0 because it starts from rest, plus 0.3 times by 80, and it turns out we have 24 meters per second squared. And then for the next part, we have to state the time for which the train is decelerating. Well, it comes to rest at the point B, so this time v is equal to 0, so we have 0 equals 24, so the idea is it starts from rest, accelerates, constant acceleration, then it decelerates, and up to here is where we have 24 meters per second. So our current velocity is 24, and because it's decelerating at 0.5 meters per second squared, we've got minus 0.5, and then we multiply this by t. And what you can see then is t is equal to 48 seconds. And then we have to sketch a velocity time graph. So if I sketch a velocity time graph of this entire situation, we've got here our velocity time graph. Now at this point we've got 24 meters per second. We know up to here we've got 80, and the time for which the train is decelerating from here to here, this is 48 seconds. So perhaps if we add in the different parts, we've got here 80, and then between these two we've got t. And then for part B, the total distance between the two stations is 4,800 meters, and using the model we have to find the total time taken by the train to travel from A to B. Well, for part B, we can find out the area of this trapezium and set this equal to 4,800, the area under a velocity time graph is equal to the distance. So we've got 1/2 times by, well, we've got here t plus the total over here, which is 80 plus t plus 48. And then we times this by 24. This is equal to 4,800. So we have 1/2 multiplied by, well, here we've got 2t plus 128. This is equal to 200. So we have t plus 64 equals 200. T is equal to 136. And so, therefore, the total time, we've got 80 seconds, plus this t, which is 136, plus this 48, and it turns out we get 264 seconds. And then for part C, we have to suggest one improvement that could be made to the model of the motion of the train from A to B in order to make the model more realistic. Well, we could have the train accelerating or decelerating at a variable rate. Question 8. A particle P moves along the x-axis at time t seconds t is greater or equal to 0. The displacement x meters of P from the origin O is given by x equals 1/2 t squared times t squared minus 2t plus 1. And for part A, we have to find the times when P is instantaneously at rest. So for part A, we've got so far x equals 1/2 t squared times t squared subtract 2t plus 1. And if I work out what this is, I've got 1/2 t to the power of 4 minus t cubed plus 1/2 t squared. And the reason I want to find out what x is like this is because I need to find out what v is, the velocity, and that's equal to the derivative of x with respect to time. So if I differentiate this, I end up with 2t cubed minus 3t squared plus t. And if I factorize out a t, I've got t multiplied by t squared minus 3t plus 1. And I can factorize this even further. We've got t multiplied by 2t subtract 1 multiplied by t subtract 1. Now, it's at instantaneous rest when v is equal to 0. So, we take our formula for v and then we set this equal to 0. And doing so, we end up with t equal 0, 1/2 or 1 second. Then for part B, we have to find the total distance travelled by P in the time interval 0 to 2. Well, what we'll do is we'll take a look at these critical values and see what's happening. When t is equal to 0, x is equal to 1/2 multiplied by 0 squared multiplied by 0 squared minus 2 times 0 plus 1. It turns out we get 0. And what we can therefore conclude over here then is there's no displacement in this case. Now let's see what happens at our next critical value. T equals 1/2. When t equals 1/2, x is equal to 1/2 times by 1/2 squared multiplied by 1/2 squared minus 2 times by 1/2 plus 1. And it turns out here we get 1/32 meters. What does this represent? Well, it represents the displacement from the origin, and that displacement is 1/32 meters. Now let's see what happens when t is equal to 1. X is equal to 1/2 multiplied by 1 squared multiplied by 1 squared minus 2 times by 1 plus 1, and it turns out here we get 0 meters. And so what does this represent? Well, it represents for us moving 1/32 meters back to the origin. Now let's see what happens when t equals 2. X is equal to 1/2 times by 2 squared times by 2 squared minus 2 times by 2 plus 1, and it turns out here we get 2 meters. So what does this represent then? Well, it tells us that the displacement from the origin then is 2 meters. And so therefore, the total distance, we've got 0 before, and then we've got 1/32. That is the displacement over here. And then we've got another 1/32. And then we've got another 0. So it turns out here, rather, we've got another 2 from here. And we get 2.0625 meters. So that's the total distance. And then for part C, we have to show that p will never move along the negative x-axis. Well, so far, we've got x, which is equal to 1/2 times by t squared times by t squared minus 2t plus 1. And I can rewrite this as a perfect square. I've got 1/2 t squared times by t minus 1 squared. And so what we can say then is, as t squared and t minus 1 all squared are perfect squares, in other words, x is always greater or equal to 0, we can conclude p will never move in the negative x-axis. Question number 9. Two small balls P and Q have masses 2m and km respectively, where k is less than 2. The balls are attached to the ends of a string that passes over a fixed pulley, as we see here. The system is held at rest with the string taut and the hanging parts of the string vertical as shown in figure 1. The system is released from rest, and in the subsequent motion P moves downwards with an acceleration of magnitude 5g/7. The balls are modelled as particles moving freely. The string is modelled as being light and inextensible. The pulley is modelled as being small and smooth. Using the model, we have to find in terms of m and g the tension in the string. Now, what we can do first of all is add on relevant information on our diagram. We've got the acceleration going downwards. So here we've got the acceleration is 5g/7 meters per second squared. We've got the weight from P, that's going to be given as 2mg. And here we've got the weight going downwards. We've got k mg. And then we've got the tensions, which are the same. So here we've got a tension T, and here I've also got a tension T. So for part A, I've got the sum of the forces, which is equal to the mass times by acceleration. And if I focus on P, I've got going downwards 2mg, subtract T, and that's equal to 2m, the mass, times by the acceleration 5g over 7. And so therefore, if I rearrange, I've got 2mg plus 10mg over 7, so it turns out T is equal to 4mg over 7. Then for part B, we have to explain why the acceleration of Q also has a magnitude of 5g over 7. Well, the string is modelled as being light and inextensible. And now for part C, we have to find the value of K. Well, if I use F equals ma, but this time for Q, I've got the sum of the forces, which is equal to the mass times by acceleration. And if I use this for Q, then I've got T minus kmg equals km times by 5g over 7. And so, knowing what T is, I've worked that out to be 4mg over 7. I subtract from this kmg, and that's equal to 5k mg over 7. So, rearranging and noticing that the m and the g's cancel, I've got 4/7 minus k equals 5k over 7, and multiplying through by 7, I end up with 12k equals 4, from which I can conclude k is equal to 1/3. Then for part D, we have to identify one limitation of the model that will affect the accuracy of our answer to part C. Well, the model does not take into account the mass of the string.